So welcome to the next lecture of selected topics in graph theory. Today we finish with we are done with colorings of graphs for this course, and we start the last larger topic that will be discussed here, namely expander graphs and introduction to spectral graph theory. So today we will give basic definitions and intuitions about expanders and basic properties. During the next lectures, there will be a deterministic a construction of an expander, and we will finish the course at the very end by proving that undirected reachability is logarithmic space, which is an algorithmic result that heavily uses graph theory of expanders. Okay, so let's go to the intuitions behind all of this. So the main idea, this is like a basic idea that probably you have seen in some places, or that is actually quite natural once you start to think about graphs, is that with a graph we can associate an algebraic object, an adjacency matrix of the graph. And if you want to think about the combinatorial properties of a graph, you can also try to understand those combinatorial properties through some properties of its adjacency matrix. And adjacency matrix, as a linear algebraic object, it has a lot of those linear algebraic properties that can be associated with it. And the idea is to try to understand how those algebraic properties of the adjacency matrix, how they project to the combinatorial properties of the original graph, and how one can be connected to the other. Right. So in this setting, we will be mostly working, and this will become clear in a moment, with regular multigraphs, more precisely deregular, where d is the degree. So a deregular multigraph is simply a multigraph where every vertex has degree d. Note here that, for example, here you've got on the left hand side, you've got the graph itself. So every vertex has degree 3 here. It has degree 4. Sorry, so this is a 4 regular multigraph. Actually, I messed something up, I think. So let me add one more loop here, and there should be 2 there. So this is a 4 regular multigraph here, and on the right hand side we've got the adjacency matrix of this multigraph, which is just a n times n matrix, where on entry in, say, row I and column j, you put the multiplicity of the number of edges between vertex I and vertex j. Right. So for example, if this is the vertex number 4 and vertex number 1, right, this vertex and this vertex, then this one signifies that there is one edge between vertex 1 and vertex 4. So observe that here multi-parallel edges like they are counted several times in those entries. So for example, this 2 corresponds to 2 edges between vertex 1 and vertex 2. On the diagonal, you have the number of loops. So we allow loops in our multigraphs. And note that contrary to some other areas in graph theory, loops contribute 1 to the degree. So you think of loop as being sort of an annotation at the vertex, saying that you can go from this vertex to this vertex again. And therefore, for example, this 2 here corresponds to the fact that vertex number 3 has 2 loops on it. Right, so then deregular means that the sum in every row is equal to d, and because the matrix must be symmetric, the sum in every column also is equal to d. All right. So then, if you have a graph, you can, from the graph G, you can get the adjacency matrix A of G, and from this matrix A of G, you can understand what are its algebraic properties. And algebraic properties of this matrix that we will be mostly interested in are the properties of its spectrum. So the spectrum of a matrix is the set of eigenvalues of the matrix. I guess that many of you had a linear algebra already some time ago. So a quick reminder, an eigenvector of a matrix is a vector, say V, such that if you act with the matrix on this vector, the matrix acts as by just prolonging this vector or shortening this vector. Yeah, so AV is equal to some lambda, which is a constant called the eigenvalue times the vector v itself. So it just shrinks or expands this vector, but preserves its direction. So these are eigenvalues. And we will try to understand the properties of this matrix A through understanding its spectrum. So the set of eigenvalues and also the set of corresponding eigenvectors for this eigenvalues. Yeah, so let's take a quick example. In our case, what will be what eigenvectors you can quite easily already see. So if G is a irregular multigraph and say A is its adjacency matrix, then you can very easily see already one eigenvector. This eigenvector will be of crucial importance for us later on, namely the vector of all ones. Yes. So well, which corresponds to putting a 1 on every vertex of the graph. So then if you think about what does it mean to multiply this vector by the matrix, this means essentially that you count how many, you count the sums in every row of the matrix. And because the graph is irregular, every time you count, you sum a row, you will get D in total. So you will get D times the all ones vector as a result. So then the vector of all ones is always an eigenvector of your adjacency matrix with the corresponding eigenvalue equal to D. So this will be important in later. So note also that because we are talking about undirected multigraphs, the matrix A is a symmetric matrix, right? So A is equal to A transpose. Okay, so if you think about what you know from your linear algebra course about symmetric matrices, real matrices, and their spectra, probably there was one theorem that you should have seen during your first year about such matrices. So the theorem says that whenever you have a symmetric matrix over reals, then you can always find an orthonormal basis of eigenvectors of this matrix. So more precisely, you can find some vectors v1 through vn, and the corresponding eigenvalues lambda 1 through lambda n, such that these vectors form an orthonormal basis of the space R to the n. So more precisely, each of them has length 1, so L2 norm equal to 1, and they are pairwise orthogonal. Yeah, so their pairwise scalar products are equal to 0. Cross products are equal to 0. Just to remind you, a cross product or a scalar product of two vectors u and v is simply defined as the sum of ui times vi, where ui is the if entry of vector u. Yeah, and the scalar product equal to 0 means that the two vectors are orthogonal. And then each of them must be an eigenvector with the corresponding eigenvalue equal to lambda I. So if you act with matrix A on this vector vi, then you get the same vector vi, only scaled by the corresponding eigenvalue. Good. So this is something that you should probably have seen during your linear algebra course, but I thought that I will actually give you a proof of this theorem. Before I give you a proof of this theorem, let's think about it, how this looks actually geometrically. So here is this orthonormal basis. Yeah. So here is a vector v1, here is vector v2, here is vector v3. I cannot draw in more dimensions, so let's stick with R3. And then what the matrix A does with those vectors is that, for example, v1 is being maybe shortened to half, maybe v3 is being prolonged to twice, and maybe v2, I don't know, maybe it is prolonged a little bit, right? So this is lambda v1 and so on, which is the result of applying A to v1. And then whenever you take any other vector in your space, you can always write it as a sum of its you can always write it in this orthonormal basis v1, v2, v3. So you can write it like that. Yes, and then by linearity, how A acts on this vector, it essentially acts on every coordinate separately. So this coordinate is being multiplied by lambda 1, this coordinate is being multiplied by lambda 2, and so on, and the last coordinate is being multiplied by lambda n. So in this orthonormal basis, your operator A, your matrix A, acts in a very, very simple way, essentially coordinate. So this is what the theorem says, and I thought that it might be good to actually remind you the proof of this theorem, because many of us had a linear algebra course already quite some time ago. For some of us, it was actually literally 15 years ago. So yeah, and this proof also will be insightful in the sense that it will actually show some combinatorics of what happens, how this symmetric matrix actually does act on R to the n. So I will be proceeding with the proof in a slightly larger generality for convenience. So I will speak about an abstract linear space together with a finite dimensional linear space together that's equipped with a scalar product, with a cross product. So formally, I should say that this is a finite dimensional Hilbert space. Over the reals, there is nothing to be scared about here. Hilbert space simply means a linear vector space equipped with a scalar product. And an operator L, so an endomorphism, and a mapping from V to V that is linear, is called symmetric. Yes, if it satisfies the following inequality. So whenever you have two vectors u and v, if you take a scalar product of u and v, and to one side you apply L, that's the same as if I moved application of L to the other side. So this is like an abstract definition of a symmetric endomorphism of a Hilbert space. So just to make it more real and more concrete, if your vector space is simply R to the n with the classic scalar product, and your linear endomorphism is simply applying some matrix U, where the matrix is symmetric, then you can easily see that actually this equation holds, right? Because what is L? What is the cross product of U V, where to L I apply to U I apply the operator L, where well, LU is the same as simply multiplying U by the matrix A. So the cross product of U and V, this is actually the same as say taking U transpose V. That's the classical thing. So this is the same as this. So AU transpose V. So now I can move this with this transposition under the bracket, so I can write it like this. So U transpose A transpose V, but A transpose is the same as A because A is symmetric, right? So now I have this, and I can now put the brackets here and see that AV is the same as my operator L applied to V. Yeah. So I moved now the operator L from one side of the scalar product to the other side of the scalar product. And like every finite dimensional Hilbert space over the reals can be, if you take any orthonormal basis of the space, it can be understood isomorphic to R to the n with the classic, with the standard scalar product. So actually, this is a precise characterization of what those symmetric operators, symmetric endomorphism look like. They actually correspond to symmetric matrices. Good, but it will be convenient to work a little bit more abstractly, so I will abstractly work with such a symmetric endomorphism. So first of all, we will use two observations, and the first observation is that well, if we want to find an orthonormal basis of consisting of eigenvectors, then at least we need to find at least one eigenvector. Good. So how to find at least one eigenvector of such a symmetric operator, symmetric endomorphism. So let's get more real in the sense that we have this abstract finite dimensional Hilbert space, but actually if I take an orthonormal basis of this vector space, then this vector space is isomorphic to simply R to the n, and my symmetric operator L is simply application of some matrix A, right? So now with this matrix A, I can associate the characteristic polynomial of this matrix. That this is the standard idea. So I simply take this matrix A and I subtract a lambda times the identity matrix. So this is a polynomial in lambda, P of lambda. It's the degree of P, the characteristic polynomial is at most n, the space or the dimension of the space. And then if this is a polynomial of degree n, from the fundamental theorem of algebra that says that every n degree n polynomial over the complex number has a complete set of roots. This means that this has a complete set of roots. So in particular, it has at least one root over the complex number, so lambda 1. Yeah, so this means that if lambda 1 is the root of the characteristic polynomial, then the determinant of A minus lambda 1 I is equal to 0, which means that this matrix is singular, it has a non-trivial kernel, and any vertex in this kernel, it satisfies that A minus lambda 1 I times V1 is equal to 0, which you can rewrite as simply, if I act with matrix A on V1, this is the same as scaling V1 by lambda 1, right? So we have now one eigenvector at least. However, this is an eigenvector over the complex numbers, yes? And it may happen that actually lambda 1 is a complex number. However, this is not the case. I will now prove that actually lambda 1 is a real. So every eigenvector of a symmetric matrix or matrix corresponding to a symmetric operator is actually real. And for this, let me look at the following quantity. So I take A. Here, this is my matrix. On one hand, I multiply by the vector V1, and on the other hand, I multiply by the vector V1, however, transpose and conjugate. Okay, so on one hand, what I have is that I can put the brackets like that. Yeah, so I can write here V1 conjugate transpose times and A V1. This is the same as applying L, or actually, well, we have already this. So this is the same as times lambda 1 V1, right? So this is, I can write lambda 1 times V1 conjugate transpose V1. And this you can easily see that this is the same as lambda 1 times the L2 norm of vector V1 squared. Yes, because here you will always like a coordinate-wise add the coordinate times the coordinate transpose conjugate, which gives you the L2 norm of the coordinate in the complex numbers. Good. So this is on one hand. On the other hand, you can put the brackets in the other place. So you can put the brackets like here. And now we use the fact that A is a symmetric matrix. If L was a symmetric operator, you can easily see that A must be a symmetric matrix. And then also A is a real matrix, so it doesn't. It's not a problem to just conjugate it. Right, so let me maybe rewrite it so that you can see it. So V1 conjugate transpose A conjugate transpose times V1. And now I can put the brackets here. Yeah. So when I put the brackets here, this is the same as A conjugate V1 conjugate, all of it transposed V1. And now you see here that if A V1 is lambda 1 times V1, then N A conjugate V1 conjugate is simply V1 conjugate but multiplied by lambda 1 conjugate. Yes. So this is equal to lambda 1 conjugate times again V1 L2 norm square. Right. So now V1 was a non-zero vector. I took any non-zero vector from the kernel. So I can now cancel out this and see that lambda 1 is equal to lambda 1 conjugate. Good. So in this way, we have proved that that every eigenvalue of our matrix will be a real eigenvalue, and therefore, if I have a real eigenvalue, I can take any vector from the kernel over the reals of this singular matrix, and it will be a real eigenvector. Good. So this was observation number 1. We have proved that there is at least one eigenvector. And now the second observation, this is actually a crucial observation, is that if I now have this one eigenvector v1, and I look geometrically at the space that is orthogonal to v1, yeah, so this is let W be the subspace of vectors that are orthogonal to v1, then actually applying my symmetric operator L to W preserves W. So in other words, W is an eigenspace of our operator L. Yes. So whenever I apply L to any vector from that is orthogonal to v1, I get again a vector that is orthogonal to v1. Okay, so let's prove it. So I've got some vector W that is orthogonal to v1. Yes. So W v1 is equal to 0. I need to prove that if I apply L to it, I also want to get 0, yeah, because this will actually prove that the result is also in the subspace orthogonal to v1. Good, but now our operator is symmetric, so I can move L to the other side. Yeah, lambda L v1. But now LV1, because v1 was an eigenvector, yes, this is the same as lambda 1 times W v1. Yeah, because what L does with v1 is just scales it by the eigenvalue lambda 1. Yeah, but now our assumption was that W was orthogonal to v1, so this is 0. Yeah, so we have indeed proved that when I apply my symmetric operator on any vector that is orthogonal to v1, I get again a vector orthogonal to v1. Good. So what is now the conclusion? If I take my operator L and I restrict it to the subspace W, it is again an endomorphism of this subspace. Well, we have just proved it here. And it is symmetric, right? Because, well, it was symmetric on the whole space, so it must be symmetric also on the subspace. Okay, so now I can apply induction and find on this Hilbert space, finite dimensional of dimension 1 smaller, an orthonormal basis of base consisting of eigenvectors. All these vectors are in the subspace that is orthogonal to v1. So then I can add v1 to the thing and get an orthonormal basis consisting of eigenvectors. Okay, I did not say why their norms are equal to 1, but of course I can scale them so that they are of length 1. So this is the proof. I hope I went quickly through this because I hope that many of you already remember it from your linear algebra course, but I want to go through it because it actually shows some internal combinatorics of symmetric endomorphism, or rather symmetric matrices. Good. Are there any questions to this proof, or otherwise, if you are happy with the proof, please put a +1 in the chat. Okay, I see quite a number of +1, so I hope that this is okay. If you missed something in here, probably there are some notes from your linear algebra course that can refresh the memory here. But what will be actually important out of this proof later on is this observation, that whenever I have got an eigenvector, then the subspace orthogonal to the eigenvector is an eigenspace of the symmetric matrix. Okay, so let's now think about how this applies to our situation of deregular multigraphs and their adjacency matrix. So I've got a deregular multigraph again, and I look at this adjacency matrix, and from our theorem, we understand that if I look at the spectrum of this, I have all the eigenvalues I need. and all of them are real. So I can have eigenvalues lambda 1, lambda 2, up to lambda n, and they can be ordered like this. So lambda 1 is the largest eigenvalue. Yeah, and we will try to understand the properties of the matrix through the properties of the spectrum. So first of all, let's see some easy lemmas about it. So first of all, clearly we have already seen that D, the regularity of the multigraph, is one of the eigenvalues. Yes, and because I have the eigenvector all ones, which exactly corresponds to this eigenvalue. Good. So this is lemma 1. I claim that this is actually an extremal eigenvalue, the largest one. All of the other eigenvalues actually are in the interval between minus d and d. So on the line, this picture will appear a lot later. You have here d, you have here minus d. You will have one largest eigenvalue equal to d, and all the other eigenvalues will be in here, somewhere in this interval. Good. So why so? Why the eigenvalues cannot be larger? Well, let's look at any vector v. Let's apply a to it, and let's see what is the one norm of the vector that we get. Just recall that the one L1 norm of a vector is simply the sum of the absolute values of the coefficients. Yeah. Good. So let's rewrite it so that we understand it. If I write it like this is sum from I equal to 1 to n, and now I need to understand what is a times the if entry of a times v. So this is the sum from j equal to 1 to n aij times vj. I hope I did not miss anything. Aij is of course, ij entry of the adjacency matrix. So now this I can bound by the sum like that. Aij times vj. Yes. And now the crucial operation of the of all of the combinatorics, changing the order of the summation. So let me first sum over j, and then I can put j in front. Yes. Here I've got sum aij over all i's, and now observe that your matrix is now deregular, right? So this sum is always equal to d. So this is d times the sum over j of vj, which is exactly the L1 norm of the vector v. Yeah. So this means that in the one norm, our matrix A cannot expand any vector by more than d. So in particular, there cannot be any eigenvalue that is larger than d in absolute value. Good. So again, let's redraw this picture because it's important. There is one eigenvalue here at d, and all the other eigenvalues here sit somewhere here inside this interval between minus d and d. And the crucial thing that we will actually look at is how well these two guys are concentrated, how these other guys are concentrated around the zero, meaning how spread they are in this interval. In particular, what we will be interested in are the following two quantities. First quantity is lambda 2. So this is lambda 1, the largest eigenvalue, and lambda 2 is the second largest. And another quantity is this something I will call lambda, simply, which is the maximum of the absolute values of lambda 2 and lambda n. So what is the total span in absolute value that all these other eigenvalues can attain? And these two quantities, they can be also understood in algebraic terms, so using the A understood as an operator. I think that this inequality can be easier to understand. So I claim that the maximum absolute value of this one and this one is equal to the following quantity. I take all the vectors that are orthogonal to 1. So I look at the vector of all ones and I take the subspace that is orthogonal. And I look at how much at most the operator A can expand the norm of the L2 norm of the vector. Yeah, so I take the ratio between the L2 norm of the vector after application of A divided by before the application of A, and I take it over the subspace orthogonal. So why is it so? Well, inside the subspace, recall that this subspace is actually an eigenspace of your operator, and how the operator, how the matrix A acts on the subspace. Well, there is this orthogonal basis of vectors v2 up to vn, yes, and A applied to say alpha 2 v2 plus alpha n vn works by just multiplying by those eigenvalues. Yeah, and this is an orthonormal basis. So if you think about it, if you have a vector that has certain coordinates in this orthonormal basis, and every coordinate gets expanded by at most lambda, which is the largest absolute value of these things, then the norm of the vector cannot expand by more than lambda. Good. So this justifies this equality. Well, it actually justifies this inequality, but of course the equality is attained for the eigenvector corresponding to either lambda 2 or lambda n, depending which eigenvalue is larger in absolute terms. This equality, well, you need to look at it a little bit closer. So let's say that u is the vector, sorry, u is the vector u1 up to un, or maybe I will just write it like this again, that u is a vector alpha 2 v2 plus alpha n vn. I do not write, of course, this alpha 1 v1 because u is from the subspace orthogonal to all ones, and all ones is equal to the eigenvector v1. Yeah, so this term here doesn't appear due to this orthogonality. Yeah, so then this what is u? What is u scalar product u, which is the same as the second norm square here. Well, this is alpha 2 square plus and so on plus alpha n square. This is just Pythagoras theorem essentially, right? But well, written in a scalar product form. And now what happens if I take AU and multiply by it by u? AU is the same as like lambda 2 alpha 2 v2 and so on plus lambda n alpha n vn. And now if I take a scalar product of these two, because this is an orthonormal basis, I need to simply multiply this by this and this by this. Yes, so pointwise. So I get that this is equal to what? Lambda 2 alpha 2 square plus and so on plus lambda n alpha n square, right? So now if you take a quotient of these two terms, this term and this term, you can easily see that this quotient, because these terms lambda 2 square and so on, they are non-negative, this quotient will be always upper bounded by the largest possible coefficient here, which is lambda 2. And again, the maximum will be attained for a vector that is for any vector that is parallel to v2, to the eigenvector corresponding to lambda 2. Good. So these are the two observations that essentially express those two extremal eigenvalues within this smaller spectrum through some algebraic terms. Good. Any questions about this? Good. If not, then maybe I will continue. And then yeah. So what we will be actually interested in on this picture are the following two quantities: the spectral gap and the absolute spectral gap. So the spectral gap is probably easier to understand. So if here is this d equal to lambda 1, the largest eigenvalue. Here is minus d, and here are all the other eigenvalues. The spectral gap is simply the gap between the largest and the second largest. Yeah, so this is d minus, which is lambda 1, minus lambda 2. So how much space is there between lambda 1 and lambda 2? The absolute spectral gap is that how much space is there between the borders of this interval and then the closest other, the closest eigenvalue inside. So the absolute spectral gap is d minus the maximum of lambda 2 and lambda n, which essentially says that you've got absolute spectral gap equal to delta if here you've got delta and here you've got delta on the sides. And these two quantities, the spectral gap and the absolute spectral gap, this will be key like parameters of the spectrum of a matrix that will somehow govern the combinatorial properties of the graphs that we will be speaking about. And we will say that a graph G is an n delta alpha expander, where alpha is a is some number from 0 to 1. If this is a graph that has n vertices, that is deregular, as we always assume here, and where all the eigenvalues of the adjacency matrix, apart from of course the largest one, are in a smaller interval, the interval between minus alpha d and plus alpha d. So in other words, again on this picture, this looks like that here is this one eigenvalue d, here is 0, here is minus d, but apart from this, all the eigenvalues are in some smaller interval between minus alpha d and plus alpha d. So they are somehow alpha concentrated around the 0. Yeah, and then and the alpha expander will be a good expander for us if alpha is actually strictly smaller than 1, in a sense that they are really separated from the borders of this interval minus dt. So all of this game will be about constructing and using good expanders in this sense. And there are two main theorems that probably we want to know after the series of lectures. First of all, that a random graph is a good expander with high probability. So there are, of course, some caveats. What does it mean, a good expander? Here you need to understand, and also what is a random deregular graph. So this we will be doing during the tutorials next week. This is essentially a good exercise in probabilistic method and trying to estimate what are the quantities in a random graph. So the intuition is that if you sample a graph uniformly, a deregular graph, it will be a good expander. And on the other hand, the important fact is that you can actually construct expanders deterministically. So we will prove actually in 2 weeks, I think, that there is always an nd 1/2 expander for every n and some fixed constant d. Yes, and such expanders can be constructed deterministically. So in some sense, the conjunction of this theorem tells you that that expanders are sort of pseudo-random objects, in the sense that a random graph is an expander with high probability, and on the other hand, you can construct deterministically graphs that still satisfy good expansion, have good expansion properties. So in some sense, these expanders are very often used as pseudo-random objects for various determinization arguments. So they can be used as pseudo-random objects where various random behavior still is there and can be somehow quantified. And on the other hand, you can actually construct them. You do not need to sample them. So various derandomization tools, they often use expanders as a basic technique. Good. So during the remainder of this lecture, I want to give you some intuition about those pseudorandom properties, and in particular, what kind of pseudorandom properties we will be interested in. But maybe before we go further, maybe there are some questions, and or if there is no doubt, then maybe put a +1 if you are happy with everything so far.
I have one question.
Yep.
Namely, is it clear that lambda2 is positive?
It is not clear, and it might be not true.
Because in previous propositions, sorry for late question, but in previous proposition, when you were proving that lambda2 is satisfies this equality.
You mean this one?
Yeah.
Yeah. I never used the fact that lambda2 is positive in this argument.
But if lambda2 is negative, then this maximum will be 0. I know this.
You mean this? That I need to assume that
okay.
It's non-zero?
Probably,
yes,
yeah.
Okay.
Yeah, sorry
I needed to assume this
case.
in order to for the fraction to be well defined.
Oh, yeah. Okay, yeah.
Yes. It can be that that lambda2 is negative, and actually, if you take a clique, say a clique of size d+1, which is then d regular, then its spectrum will look like this: that there will be one eigenvalue at d, as far as I remember, and then there will be d other eigenvalues at -1. Yeah. So this so here will be 0, and there will be d eigenvalues at -1. So then all the other eigenvalues apart from lambda1 will be equal and equal to -1. So this is a situation where the second eigenvalue is actually negative. Good. Any more questions?
Is being an expander a structural thing in any way, or is it just this abstract property?
You mean that there is some decomposition or something?
Like anything that tells us how expanders look like?
I think that at the end of this lecture, there will be an answer to this question. In some sense, yes. Okay. So being an expander in this sense has strong implications about the combinatorial properties of the graph.
Okay.
Yeah, and we will see such things later. Good. Okay, so let's then go to some pseudorandom properties of expanders. And the first property that I would like to show you is something called the expander mixing lemma. And this tells you about, let's say, the pseudorandom behavior of edges in an expander. So imagine that you've got an ND alpha expander, yes? And you've got some two subsets of vertices. So let's think for now that they are disjoint. They do not need to be disjoint in the proof, but let's say that they are disjoint for simplicity of thought. Good. So these are two subsets of vertices. And let's think about all the edges with one endpoint in S and second in T. So here is your graph, here is set S, here is your set T. And you look at all those orange edges that have one endpoint here and the second endpoint there. So how many edges do you expect there to be in a random deregular graph? Well, there are S times T in total pairs there, and every edge appears there with probability d over n, if this is a deregular graph. So you expect this number of edges there in total in a random graph, d over n times S times T in expectation. And the claim is that if this is a good expander, then the actual number of edges for any set of pair of sets of vertices S and T will not differ too much from this quantity. Yeah. So the absolute, so the distance between the difference between the actual number of edges and this expected number of edges is at most this quantity. So alpha times d, yes, times the square root, the geometric mean of the sizes of S and T. Yeah, so you see here that the better expander you have, the smaller alpha, the more concentrated are the eigenvalues, the better, the sharper, the better estimate you have here. Yes, the smaller is the difference between the pseudo-random behavior and the actual random behavior. Good. So this is the lemma that we are going to prove, and this proof will also show you a basic technique of proving things with expanders. Okay, so let me look at the following two vectors. So one vector is the vector of ones on the set S. So this is a vector where a column vector where I put zeros and ones, and the ones are on the elements of S. Yeah, so you can view the coordinates in your vector space as being, of course, labeled with the vertices of your graph. Yeah, so this is one on the set S, and similar one on the set T is I put ones on the elements of the set T and zeros otherwise. So then, how can I phrase what is the number of edges between S and T with one endpoint in S and the second in T? I can phrase it like this. I put A in front, and on the right-hand side, I multiply by the all ones on T vector, and on the other hand, on ones on S transpose. Why so? Because, well, if I have this square matrix A here, and I multiply by this one T here and one S transpose here, then actually those ones here and those ones here exactly will make survive those entries of this matrix that correspond to rows and columns belonging to T and S respectively. Yeah, so in total, in this whole sum, I will sum up only the elements of the matrix that correspond to the possible edges between S and T. Yeah. So now this is the same as A transpose because A is symmetric. So in particular, I can write this down as this scalar product. Yeah, so one on T multiplied by one on S, but with the matrix A applied to it. Good. So now we have understood the number of edges between S and T through an algebraic expression, through some scalar product. And now comes the main trick of expanders, and you will be completely fed up with this trick after this series of lectures. Namely, I take my vector, say 1 on S, and I now decompose it into two orthogonal vectors. One will be a vector that is parallel to the vector of all ones, and one will be a vector that is orthogonal to the vector of all ones. So in other words, if here is the vector 1 on S, yes, here is the direction of the vector of all ones, yes, then I decompose it into two orthogonal vectors. One is the projection of this vector on the direction of all ones, and one is the one that is perpendicular. Yes, one S perpendicular. Yeah. So now one S will be decomposed into the sum of those two orthogonal vectors. So how do you actually express this projection? The easiest way is to use the following formula. So if you want to project a vector say 1S onto the vector of all ones, you take all ones and you multiply it by the following coefficient. You take the scalar product with all ones here, and you divide by the scalar product of all ones together with itself. And it is quite easy to understand why this formula for a projection onto some direction is true, because this is a vector that will be parallel to all ones, right? Because, well, it's essentially all ones multiplied by some coefficient. However, it has this property that if I take all ones on S and multiply it like cross product, take a cross product with all ones, then this will be the same as taking the cross product of this parallel thing. And this coefficient is chosen so that this equality holds, right? Because, well, I have essentially put just this coefficient there explicit. Yeah, if I take a cross product with all ones here, this cross product of all ones will with itself will cancel out, and I will get this coefficient at the end. Yeah, so this is a easy to remember formula for projecting a vector onto some direction. Yeah. So now, what is actually this animal? 1 on S cross product 1. Well, I just sum up the coefficients in the entries in 1S, so I get simply the size of S because that many ones there are in this vector. And if I take a cross product of 1 with itself, I get N, right? So this is just the vector of all ones multiplied by the coefficient size of S over N. And the parallel part, well, it's simple now. It's just the rest. Yeah, so this is a 1 on S with the parallel part subtracted. And now from this equality, you can easily see that the following equality holds, that this vector is orthogonal to the vector of all ones. Good. So now we have decomposed the ones on S into those two orthogonal vectors, and similarly, I can decompose 1 on T into those two orthogonal vectors. Good. So now comes the calculation. Okay, so we now want to estimate how many edges there are between S and T, and we have already argued that we can write it down as this algebraic expression. Yeah, so 1 on S cross product 1 on T, but to one of those two I apply A. Yeah. So now each of those two guys, 1 on S and 1 on T, I have written as a sum of two vectors. Yes. So I can use the bilinearity of the scalar product and write it down as the sum of those four terms. Yes. So in two of those terms, I've got parallel, perpendicular, perpendicular, and there are two of them that are mixed. But fortunately, some of the stuff here cancels out, because, for instance, this guy is parallel to the vector of all ones. Well, it's just all ones multiplied by some coefficient. On the other hand, this vector, 1S perpendicular, it is perpendicular to all ones. And recall that A acts on the subspace of the space of vectors perpendicular to all ones is an eigenspace of the matrix A. Yeah, so this whole vector after application of A, this will also be perpendicular to all ones. So this is a scalar product of two guys that are actually orthogonal to each other, because one is in the direction of all ones and one is in the perpendicular direction, in the orthogonal direction. So this whole term is actually equal to 0, and the same here. Yes, this will actually be something parallel to all ones, and this will be orthogonal to all ones. Yeah. So fortunately, two of those terms cancel out. So we are left with two remaining ones. One of them is simple, right? This one is simple because we actually know what is this animal. Yeah, with this animal is, well, okay, maybe I'll just follow what I wrote here. So first of all, A, like this animal here, 1S parallel, this is something that is parallel to all ones. And A, yes, all ones is an eigenvector of the matrix A with eigenvalue D. Yes, so A times this thing. Yes, this just multiplies it by D. Yeah, so this term is equal to this here, right? Because this thing is just D times all ones on S parallel. And this term I just rewrote. But now we understand what is this. Yes, this, as we noted here, this is just all ones times S over N. And this is all ones times T over N. Yeah. So now this whole animal here is equal to this. Yeah, because, well, you have S times T over N squared, but then you have also trailing. So you've got you've got D times S over N times T over N times 1 cross product 1, but this is equal to N, so you get exactly this. Yeah, and you've got this remaining term. Yeah, of the two orthogonal vectors. Good. So we have already found this this random behavior term, right? D over N times size of S times size of T. Yeah. So in order to prove what we wanted to prove, that the difference between the number of edges between S and T and this expected number of edges is at most this, it suffices to prove that this sort of error term, the term corresponding to the cross product of the orthogonal parts, yeah, this is bounded by what we need, yeah, in absolute terms. Yeah, that the absolute value of this cross product is at most alpha times D times the geometric mean of S and T. Good, and this will be actually pretty easy. This will be a brute force estimation. So I need to upper bound this cross product, and by Cauchy-Schwarz inequality, the absolute value of a cross product is at most the L2 norm of one times the L2 norm of the second one. Yeah? Okay, so what is the L2 norm of this animal here? Well, this vector here, the vector 1 as perpendicular, this is perpendicular to all ones. Yeah? It is in this subspace where A acts has all the eigenvalues significantly smaller than D. Yeah. So as we noted actually here, yes, in the subspace, if I apply A, the length of the L2 norm doesn't grow by D. It grows actually much better. Yes, it scales by at most alpha times D. Yeah, because this is the second eigenvalue up to the absolute value. Yeah, so here we are using the fact that we are now looking at a vector that is in this space where A is only scaling by small numbers. Yes, it's not scaling by the whole D, it's scaling by at most alpha times D. Yes, so now this L2 norm of A perpendicular part is upper bound by alpha times D times the norm of this vector. Now this was the one of the components of an orthogonal decomposition of the vector 1s. So definitely this L2 norm will be not larger than the L2 norm of the whole vector 1s, and similarly this. And now, what is the L2 norm of the vector of all of ones on S? Well, essentially, you add up S1s. If you now write what is this L2 norm using Pythagoras theorem, you will add up the size of S1s and take a square root. So this animal is simply the square root of the size of S. And similarly, this animal will be the square root of the size of T. And we are done, because this is what we wanted. Good. So to sum up, what happened in this proof is that we took the original combinatorial notion, we understood it through an algebraic notion, we applied the decomposition into the parallel part and the orthogonal part, and we understood that the parallel part corresponds to expected random behavior, while the orthogonal part is somewhat an error term in some sense that is small if the spectral properties are good. Yes, that in this error term is essentially confined to this subspace that is orthogonal to the vector of all ones. And if our operator has good spectral properties on this subspace, then we can control this error term much better. And this is somehow a theme that is always there in expanders. You will always decompose things into sort of expected random part, that is the part that is parallel to all ones, and the orthogonal part, and the orthogonal part is the error term that you need to bound somehow. And the spectral properties of the matrix are used to bound this error term. Good. Are there any questions here? Or if you are happy with this proof, please put a +1. Okay, there are some +1s, but not so many of them. Maybe I can clarify something if there is a need. Okay, there is a number of them. So okay, but maybe there are some doubts here. Okay, if not, then let me continue with this. And the second thing I want to show you is another example of this pseudo-random behavior of expanders. And I think that this even better showcases why expanders are good pseudo-random objects. Namely, we will look at random walks on an expander. So again, imagine that I've got some graph G that is a D-regular multigraph. And I'm looking at the adjacency matrix of this. And if I have some vector x from R to the n, let's say, I can think of it as a distribution of weights on the vertices. Yes, that maybe here are the vertices of your graph. And maybe this guy has vector has weight 1, this maybe has weight 2, this has weight -3, maybe here is 1/2, and so on and so on. Yeah, so this will be actually x1, this will be x2, x3, and so on. This will be the corresponding entries of the vector x. So now you can take this vector of weights on the vertices and you can apply the matrix A. So how you can understand this algebraic expression in combinatorial terms. Essentially, if you look at this multiplication, what happens is that whenever you've got some vertex v, what this multiplication happens in the row corresponding to the vector v is that it looks at all the neighbors of vector v. These are the vertices where the corresponding columns have non-zero entries, and you collect the weights from all the neighbors. Yeah, so here we've got some xu, then this xu is sort of sent to this vector v. Here we've got some xu prime, this weight is sent to this vector v, and you sum up all these weights that are sent to this thing, and this is your total, this is your final weight corresponding to v in A times x. Yeah. So on one hand, you can think that a vector v collects the weights from all its neighbors. On the other hand, equivalently, you can think that every vertex u sends its weight to all its neighbors. So in total, the total weight is multiplied by d, and this exactly corresponds to the fact that that this is a d-regular multigraph. Yeah, because every vertex takes its weight and multiplies its default and sends it to all its neighbors. Yeah. So maybe this multiplication is not that nice for the purpose of understanding this. So let us scale, or rather normalize, the adjacency matrix by multiplying it by factor 1/d. Yeah. So now, so like every entry of the matrix is then multiplied by 1/d. So what actually now happens is that the sum in each row is now equal to 1, not equal to d. So you can easily see that all ones is now an eigenvector with eigenvalue equal to 1. Yeah, so this is actually preserved by the matrix. And well, if you multiply the whole matrix by 1/d, you essentially scale the whole spectrum by 1/d. So the spectrum is now in the interval between -1 and 1. Yes, and if it was an alpha expander, then it would be actually minus alpha alpha. Yeah. So now you can start to think, okay, so we have some weight distribution before, and I can think about this matrix A acting on a weight distribution on the vertices. And now I can think, well, weight distribution, maybe probability distribution. Yeah, so let's look at probability distributions on vertices, which are just, well, distributions of weights that are non-zero, and they sum up to 1. Yeah, so this is, you can think of it, let's sample a vertex in a graph, and these are the probabilities that a particular vertex is sampled. They correspond to the entries of this vector p. Yeah. So for example, if our sampling picks one vertex deterministically, this will correspond to a vector that has 1 on this coordinate and all the other coordinates are equal to 0. So now what happens if I take our normalized adjacency matrix A tilde and apply it on some probability distribution? Well, I will get again probability distribution because the total weight is then preserved, yes, and I cannot definitely get any negative entry because everything here is positive. So I will again get a probability distribution, right? So this is again a probability distribution. And you can understand it combinatorially as follows. So taking vector P, yes, it sort of corresponds to a random experiment where I can just put an agent on a random vertex of a graph according to the probability vector P. Yeah, I sample a vertex like that. And then multiplying it by this probability, this normal adjacency matrix corresponds to, I now look at my agent and I pick one of the incident edges uniformly at random, each of them with probability 1/d, and I traverse this edge. And therefore I end up with a possibly different vertex. Yes. And now you can easily see that this A tilde and then normal adjacency matrix of the graph times the probability vector P is the resulting distribution. Yes, where my agent will be after this experiment. Yeah. So in other words, this normalized adjacency matrix is nothing else than a matrix of the Markov chain associated with G, of Markov chain of randomly walking on the graph. Yeah. So in every step, you uniformly at random choose an edge incident to a vertex and you traverse this edge. So in particular, if I start with some probability distribution P and I apply my matrix K times, this corresponds to making K steps in the random walk. So first placing the agent on some vertex of a graph according to the distribution P, and then making K steps of the random walk, right? So now comes the main idea of why good expanders are good with respect to this kind of random walks. And the idea is here that good expanders are rapidly mixing. In the following sense. Imagine you've got an ND alpha expander, yeah, where alpha is pretty good, it's small to 0. Yeah? And you've got some original probability distribution on the vertex that maybe there's simply one vertex that you can put the agent on deterministically, but in general, there can be various probabilities of various vertices. And let Pk be the probability distribution after applying K steps of the random walk. Yes. Then I claim that in L2 norm, the Pk, the probability distribution after K steps, converges to the stationary distribution, to the distribution where every vertex is with probability 1/n. It converges to this very quickly. So in L2 norm, the difference between these two vectors, these two distributions in after K steps is at most alpha to the K, where alpha is our ratio of the expander. Yes, it's so the better alpha you have, the quicker the Markov chain converges to the stationary distribution in L2 norm. Yeah. So this is exactly the intuition that is behind a lot of applications of expanders. That the random walk on an expander is rapidly mixing. It very quickly converges to sort of very well balanced distribution of probability. Yeah. So after only few steps of the random walk, you really can be anywhere in the graph with sort of equal probability. Good. Any questions before we converge to the proof at this point?
Does it imply that expander is connected graph?
It does, and you are already spoiling one of the exercises from tutorials. but not too much.
Sorry for that.
So yeah, but yes. In particular, if you start in any vertex, after some number of steps, you can be anywhere. Good. So let's go to the proof. So the proof will be again simple and will be based on the same principle. Yeah, you've got the initial probability vector p0. Yes, you've got this vector probability pk after k steps, and we already observed that pk can be expressed as p0 with this matrix of the random walk applied k times. And we play the same game as before. We take the original distribution p0 and we decompose it into the parallel part and the perpendicular part. The parallel part is the projection onto the direction of the all ones, and the perpendicular part is the rest. Yes. So the projection on the part parallel to all ones, it can be again expressed using this this formula. So here you've got n, right? Because well, it's 1 times 1 scalar product is n, and now p is a probability distribution. So the scalar product of p and 1 just sums up the entries of 1, and they sum up to 1, right? So that the parallel part is just the vector of all ones multiplied by the coefficient 1 over n. Good. So now, what does it mean to take our initial probability distribution P0 and apply our normalized adjacency matrix k times? Well, by linearity, I can apply it on the parallel part and on the perpendicular part separately. And what happens on the parallel part? Well, this parallel part is actually 1 over n times all ones. Yeah? So in particular, it is parallel to all ones. Now, all ones is an eigenvector of the normalized adjacency matrix with eigenvalue equal to 1. It's exactly preserved. So this applying this a k times here doesn't change anything, right? Because a is being preserved by this matrix. So this is just equal to again the same vector p parallel, which is 1 over n times all ones. And here we've got this error term that is corresponding to the pseudo-random part. This is an error term that corresponds to the fact that we are not in a perfect random graph. Yeah. So in order to prove this inequality, yes, we need to prove that this error term here, yes, so this error term that is added to this random behavior in L2 norm is upper bounded by this alpha to the k. Yeah? So we need to prove this. We need to estimate upper bound the L2 norm of this of our matrix A applies to P perpendicular. But now we again use the same trick. Yeah, P perpendicular, yes, is in the subspace orthogonal to all ones. And A, the normalized A, it acts on the subspace by now contracting every vertex at most by factor at least alpha, like by factor alpha or even less, right? Because alpha was our bound on the eigenvalues within the subspace perpendicular to all ones. Yeah, so every application of the normalized adjacency matrix shrinks the vector by factor at most alpha. So I've got now this inequality. Yeah, I have upper bounded by alpha to the power k times the L2 norm of P perpendicular. Now, P perpendicular was one of the components of P in a orthogonal decomposition. So the L2 norm of this vector is at most the L2 norm of P. Now the L2 norm of P, because this is a vector of this is a probability distribution, the sum of pi is equal to 1. This is upper bound by the L1 norm. This is easy to prove because, well, you need to prove that the sum of pi square is at most the sum of pi. And you can easily see that if you now here in this inequality take both sides to the square, you will see here sum of squares, and here after opening the bracket, you will see sum of squares plus some other stuff. Yes, so you've got this inequality, and the L1 norm of P is equal to just 1, right? Because it's a probability distribution. So this is upper bounded by 1. And voila, we have upper bounded the error term by alpha to the k. So this is the whole proof of this rapid mixing property of Markov chains corresponding to expanders. And this really shows that here we've got convergence to the expected behavior in the random graph plus an error term that is being distinguished and distinguished and distinguished with time by the applications of the Markov of the adjacency matrix. And we here use the fact that this that the spectrum is concentrated around 0 in order to estimate the speed of distinguishing this part. Good. Any questions about this proof? Okay, if not, then I will go now to the last part here that we will be delving more into the details during the next lecture, but I just want to sort of give a quick introduction into what we actually are interested in expanders. So we will be proving during the next lecture something called Cheeger inequalities about expanders, and this is about understanding those spectral gaps. So how good expanders are in algebraic terms through understanding how good they are in combinatorial terms. So we'll be trying to make a connection between the spectral gaps, the absolute spectral gap and the non-absolute spectral gap, and some combinatorial notions that will be called expansion in expanders. So there are two kinds of expansions corresponding to the two kinds of spectral gaps: the edge expansion, the vertex expansion. So imagine that you've got an n-vertex graph, yeah, and an edge expansion of this graph is the following quantity. So imagine you've got the whole vertex set, and you pick any subset of vertices that consists of at most half of the vertices. So the size of S is at most and half. Okay. And now let's measure how many edges are sticking out of this set of vertices. Yeah. So you measure how many edges there are between S and the complement of S. Yeah. So this is V of G minus S. And you, well, larger sets there should be more edges sticking out of them, so you normalize it by the size of S. Yeah. So definitely this is at most D, because from every vertex itself there can be at most D edges sticking out. But in sort of a random graph, you expect that if you take any subset of vertices, there should be still quite many edges sticking out of it between it and the rest of the graph. And the expander mixing lemma should sort of show you that probably in expanders, this kind of a behavior should be also preserved. So this is the edge expansion of a graph. I take this quantity and I take the minimum of it over all subsets of at most half of the vertices. So a graph has a good edge expansion if every set of vertices in these terms expands significantly. It expands with quite a number of edges. And vertex expansion is a similar notion, but a bit different. So imagine again that you've got a graph and you are taking some subset of vertices, again of size at most half. But now you measure how many vertices you can reach in one step of the random walk in some sense. So you look at this gamma of S, and these are all the edges U such that there is V from S with the edge UV present. Yeah. So you look at all the vertices here that you can reach within one step of from starting from S, but also note that the edges inside, like going from S back to S, they also count, right? So if say this vertex can be even if it is in S and but can be reached from another vertex of S, it also counts here. Yeah. So this is gamma of S. So I look how many vertices can be reached within one step from a vertex of S. I subtract the size of S and I again normalize by the size of S. And this is my vertex expansion. Yep. So again, because every vertex expands to at most d other vertices, this is upper bound by actually d minus 1 because of this here in a d-regular graph. Yeah, but and you should expect that if in a random graph I take a subset of vertices and I make one step of the random work from it, I will still see quite a number of different vertices in this way. Yeah. So observe also that this quantity, because of the subtraction, why one might think that maybe this this quantity might be negative, but this is not the case in a irregular graph. Because if I look at gamma of S, what is the size of gamma of S? Well, from every vertex of S, I can go to the other vertices, maybe to some of them multiple times through parallel edges. Yeah, but in total there are d times S edges sticking out of vertices of S, and to each element of gamma of S, at most d such edges go into. Yeah. So by double counting, you see that the size of gamma of S is at least 1 over d, because like in each element of gamma of S, d edges can meet, times the total number of edges sticking out of S. And this is just at least the size of S. So this means that this quantity here is never smaller than this quantity here. So the edge expansion in a deregular graph is never negative. Okay, are those definitions clear? Maybe some plus ones if there are no problems with them.
Maybe to clarify, in the definition of vertex expansion, this U can be from S also. Yes.
Yes.
Or
yes.
Okay.
Yes. Yeah. This is exactly what I was talking about. Okay, I see some plus ones. I hope that that for most of you this is clear. So let's continue. So now the intuition is that large edge expansion exactly corresponds to large spectral gap, and large vertex expansion exactly corresponds to large absolute spectral gap. So this is this lambda and the maximum of the two extremal non-trivial eigenvalues. Yeah. So in other words, in order to get a graph with a good edge expansion, I need to get the graph with good spectral gap. And in order to get a graph with good vertex expansion, I need to get a graph with good absolute spectral gap. So this is the intuition, and the actual quantitative expression of this intuition is through those Cheeger's inequalities, on which we will concentrate during the next lecture. So if G is a deregular multigraph, and say lambda is the maximum absolute value of the second and last eigenvalue, then the edge expansion is sandwiched between d minus lambda 2 over 2 and this funny expression square root of 2d times d minus lambda 2. Yeah, so observe that this spectral gap here you see, and the spectral gap here you see again. And similarly, the vertex expansion is sandwiched between this expression and this expression. Yes. And here you actually always see this d squared times d squared minus lambda square, which you can also write as d minus lambda times d plus lambda. Yes. This is just something between d and 2d. And here, this is exactly the absolute spectral gap. So in other words, maybe the actual quantities in this inequalities are not that important. What is important is the following corollary, that if you want to, if you would like to have the spectral gap bounded away from 0, so separated from 0 by some positive epsilon, it suffices and it's necessary to have the edge expansion separated by some delta from 0. Yeah, because these two expressions, they converge to 0 with d minus lambda converging to 0, and because they are functionally equivalent now to the edge expansion here, you see that the edge expansion converges to 0 if and only if the spectral converges to 0. And the same also applies to the vertex expansion and the absolute spectral. So this is the main corollary, but the main practical usage of this Cheeger's inequalities, probably those inequalities are the more important, because this means that if you want to construct a graph with good edge expansion or with good vertex expansion, it suffices to construct a graph with good spectral gap or absolute spectral gap. And if you are constructing a graph through some algebraic procedures or constructions, it is very often easier to control the spectral gap than to control some combinatorial properties about the number of edges sticking from any possible subset of vertices. Yeah. So what we will be using later on is that we will be constructing graphs through some algebraic constructions and then reason about their combinatorial properties, expansion properties through the Cheeger's inequalities. Good. So this is essentially all I wanted to prove, to show you during this lecture. So I hope that maybe I will have time also to prove the Cheeger's inequality number 1. But during the next lecture, we will be just focusing on proving all 4 of them because they actually are nice proofs and they show different kinds of how do you work with edge expansion, how do you work with vertex expansion, and how do you, for example, prove this inequalities 2 and 4, because then it's a little bit different game, because you need to start with some combinatorial property of your graph and reason about some spectral properties of the graph. Good. So this is what we will be doing during the next lecture. In 2 lectures, like in 2 weeks, we will prove. We will make a deterministic construction of an expander, and during the last lecture, we will use our knowledge about expanders to give undirected reachability in log space. Good. Any questions at this point? At the final step of the lecture. Okay, if not, then thank you very much for this week, and we meet in half an hour for the tutorials from chi-boundedness. Thank you.